What's up, guys? Thank you for clicking on my video. This is going to be the second review for physics. And in this review, we will be covering topics like forces, friction, forces on slopes, friction on slopes, work, energy, springs, kinematics, and resistive forces in fluids. Um, there was also problem number 6 on the practice exam that involved collisions, but to my understanding, collisions is not going to be on our exam. So I didn't make a video on that. However, if anybody does want to see a video on that, please leave a comment and I will be more than happy to make a video on it. And I probably will end up having to make a video about it either way because it'll be on our next exam. So yeah. And by the way, I think it was on problem um number 1 or 2. I don't know, but I kept calling the direction I hat. It should not be I hat. It's just I without the hat. So it's just I. So just don't listen to me when I say I hat. And yeah, please enjoy the video. And I hope something in this video helps you out. Problem number 1 says a 3 kilogram mass is initially at rest on a horizontal surface. An applied force then acts for a time of 5 seconds, resulting in the mass having a speed of 20 meters per second. Assume that the acceleration produced is constant. And part A is saying if the system is frictionless and the applied force is in the positive I hat direction, what is the magnitude of the applied force? So the first thing that I'm going to do, since we're working with forces, is I'm going to write Newton's second law. That is force equals mass times the acceleration, or the sum of all the forces, actually. But since we're only working with one force, because we're told that it's frictionless, the only force is going to be the applied force. So we have this equation, this formula right here, and now we want to find force. We know the mass and we don't know the acceleration. So in order to find force, we need to get the acceleration. Luckily, we have the initial and the final velocities, and we have time, so we can find the average acceleration, which is going to be the same as the constant acceleration in this case. So to get the average acceleration, we have to do the change in velocity over the change in time. So that's going to look like this. So velocity final minus velocity initial over the change in time. Writing that out, the final velocity is 20 meters per second. And it's going to be minus the initial velocity, but this mass started at rest, so it's going to be 0. So I'm not going to write it down. And it's going to be over the change in time, which is 5 seconds. Now we just divide. So 20 divided by 5 is going to be 4. And that is meters per second squared. That is the acceleration. So now we can plug this into here and get F. Get the force. So the force then is equal to the mass, which is 3 kilograms, multiplied by the acceleration that we just found, which is 4 meters per second squared. And solving that out we will get that the force, or more specifically the force that's applied, is going to be 3 times 4 is 12 newtons, and it's going to be in the I hat direction, in the positive I hat direction. Because we're told right here that the applied force is in the positive I hat direction, so yeah. Part B says if the system is frictionless and the applied force is acting at an angle of negative 35 degrees with respect to the positive I-hat direction, what is the magnitude of the applied force? So to do this one, we're pretty much going to do the exact same thing, or it's going to be a bit different. But so first I'm going to write Newton's second law. So the force equals the mass times the acceleration. And the force, well, the force equals the mass times the accelerations. And since in this case, again, in this part, the only force here is going to be this applied force. So the force is also going to be equal to this force applied, but only the horizontal component of it. In this problem, we don't care about the vertical component. We only care about the horizontal component. So it's going to be FA cosine of this angle, which is negative 35 degrees. And now what we're solving for is what is the magnitude of the applied force. So we're solving for this right here. So now we could set these equations equal to each other since they're both equal to the same thing. So we'll have the mass times the acceleration equals the force applied cosine of negative 35 degrees. And here isolating the force applied, divide both sides by the cosine of negative 35. I'm divide this side also, but I'm not going to write it. So now we're going to have that the force applied equals to the mass times the acceleration all over the cosine of negative 35 degrees. Now here we have all these variables. We know everything in here, so we can just go ahead and write it all down. So the force applied is equal to the mass, which is 3 kilograms. And I forgot to mention that for the acceleration, we're going to be using the acceleration that we got over here. So it's going to be accelerating at 4 meters per second squared. All of that over the cosine of negative 35 degrees. And you plug that into the calculator, you will end up with the final answer of 14.6492 newtons I-hat. In the positive I-hat direction. That is the force applied. Same problem. Now part C says if the system is not frictionless and the force applied is in the positive I-hat direction, what is the magnitude of the applied force if the coefficient of kinetic friction is 0.45? So now it's the same thing, but now we have an extra force, which is friction. So also, by the way, we're going to be using information that we got from the previous part. So the acceleration is equal to 4 meters per second, and the mass times the acceleration is equal to 12 newtons. So okay, so I'm gonna start off with Newton's second law. And like I said, so first of all, we know ma from the last problems, and in the previous problems we only had one force, but now we have two forces. So now we're gonna write Newton's we're gonna write this again in terms of the forces that we have. So we have the force applied, which is going to be in the positive I-hat direction. So we have the applied force. And then we have friction, which is going to be opposing that. So it's going to be negative. So negative kinetic friction, to be specific. And now what we can do is we can set these two equal to each other since they're both equal to the sum of all the forces. So we will have the force applied minus the force of kinetic friction equals mass times the acceleration. Now, since it's asking us, what is that? what is the magnitude of the applied force? So we want this guy, and we want him to be alone. So to get him alone, we're gonna add the force of the kinetic friction to both sides. So like that. And we have this new thing. The applied force is equal to the mass times the acceleration plus the force of kinetic friction. And we have all of these variables. So now let's just go ahead and plug everything in. So the force applied is equal to MA, which is 12 newtons, plus the force of kinetic friction. The formula for friction is F equals N times mu, which is the normal force, times the coefficient of friction. In this case, our normal force is just going to be the absolute value of the gravitational force, which is mg, which let me just write over here, which is going to be mg times mu. So for us, that's going to be the mass, which is I should have wrote that there. Oh, it's actually over here. So it's 3 kilograms times the acceleration due to gravity, which is 9.8 meters per second squared. I'm going to erase that. And then multiplied by mu, which is 0.450. Now, once you plug that into your calculator or you do that into your head, you'll get that the applied force is equal to 25.23 newtons in the positive I hat direction. The final part D, says if the system is not frictionless and the applied force is acting at an angle of negative 35 degrees with respect to the positive I hat direction, what is the magnitude of the applied force if the coefficient of kinetic friction is 0.45? So this one is going to be the same as that one. We're looking for the same thing, which is the applied force, just that now we have angles. So to do this one, we are going to start off with our sum of all the forces. Okay, so we know MA equals 12, and we also know that the sum of all the forces is going to be equal to, all the forces that are acting. So we have, in this case, we're going to have the applied force and friction. The applied force is going to be in the positive I hat direction. So we have the applied force and the kinetic friction, which is going to be opposing this applied force. So that's going to be negative the force of kinetic friction. Now, we could set these equations equal to each other. So we'll have that the force applied minus the force of kinetic friction equals the mass times the acceleration. And now what I'm going to do here, since both of these are actually going to have the applied force in them, I'm not going to isolate one or the other. Instead, I'm going to write these out. So the force applied is going to be equal to the force applied times the cosine, because we only care about the horizontal component. So that's going to be the force applied cosine of our angle, which is negative 35 degrees. And then minus the force of kinetic friction, which is going to be the normal force times the coefficient of kinetic friction. However, we have this applied force that's also going to be acting down in the vertical now. So we have to keep that in mind. So it's going to be mg, which is the normal force just by gravity alone, and then minus the applied force. So since it's in the vertical, it's going to be sine of negative 35. It's going to be mg. No, not mg. It's going to be the force applied times the vertical component of that, which is the force applied multiplied by the sine of negative 35 degrees. And this is going to be our normal force right here. And to get the force of kinetic friction, we do the normal force multiplied by the coefficient of kinetic, the coefficient of friction. So this whole thing is going to be multiplied by the coefficient of friction, the coefficient of kinetic friction in our case. So before I do anything else, I'm going to distribute this coefficient of friction. So we are going to have the force applied is, the applied force times the cosine of negative 35 degrees minus the coefficient of kinetic friction times mg, and this is going to be minus, and then when I distribute this, I should have put this in the front. I should have put that in the front so it would make more sense. But anyways, when I distribute this one over here, that's going to, and well, basically it's like a -1 right there. So I'm distributing that -1 to each of these terms, and then I'm also distributing this coefficient of kinetic friction to both of these terms. So then this is going to give me plus the force applied. Well, let me write the coefficient first. Plus the coefficient of kinetic friction multiplied by the force applied sine of negative 35 degrees. Now what I'm going to do here, also notice that I'm leaving this alone for right now because I'm not going to do anything to it just yet. Now what I'm going to do here is I have these I have two of these, and I'm going to factor them out. But before I do that, I got to get rid of this one. So I'm going to add it onto this side. So then I'll have the force applied multiplied by the cosine of negative 35 degrees. And then I'm taking that one out. So it's going to be plus mu k, the applied force, sine of negative 35 degrees. And again, this one, I'm going to add it over here. So I'm going to write it right here. So on this side of our equation, I'm going to have ma plus this one, mu k mg. And now what I'm going to do up here is I'm going to factor out this FA now. I'm going to factor out the applied force. So that is going to look like this. So the applied force is going to be, so it's going to be the applied force times the cosine of negative 35 degrees minus, not minus, plus this one, which is mu k sine of negative 35 degrees. Just like that. And I know it's gonna get like weird here, it's gonna get messy, but we have this equation which is ma plus mu k times mg equals all of this. And finally, to isolate fa, the force applied is, I'm gonna divide this side by this thing, and I'm gonna divide this whole thing by this as well. So I'm gonna divide by the cosine of negative 35 degrees plus mu k sine of negative 35 degrees. So then ultimately you'll have that the force applied is equal to the mass times the acceleration plus mu k times mg all over the cosine of negative 35 degrees plus mu k sine of negative 35 degrees. And we have all of these variables, so we could go ahead and write all of that out. So the force applied is going to be equal to the mass times the acceleration, which we have over there, which is 12 newtons, plus mu k, which is 0.450 times mg, which is 3 kilograms multiplied by the acceleration due to gravity. All of this over the cosine of negative 35 degrees plus mu k again sine of negative 35 degrees. Plugging that into your calculator, you will get that the force applied is equal to 44.969. So 44.969 newtons in the positive I hat direction. The next problem says a 3 kilogram mass is initially at rest on an inclined plane of 65 degrees. Part A says, this should be an A. Part A says, what is the speed of the mass after sliding 2 meters down the incline if the system is frictionless? So if the system is frictionless, then there's only one force that's going to be acting on here, there's only one force that's going to be causing the net force, which is going to be the gravitational force. So by using that, we can get our acceleration, and then we could just do some kinematics on this problem. So first of all, I'm going to write down what I know. So I'm going to call the distance that it slides down the ramp delta R. So delta R, we are told, is 2 meters. And we know that it's initially at rest, so the velocity initial will be 0 meters per second. And we're looking for the velocity final. And we can solve for the acceleration. We're going to solve for the acceleration here. So by Newton's second law, we have the force equals the mass times the acceleration. Since we only have one force that really matters here, I'm not going to write the sum there. So the only force is the force of gravity. So, okay, first of all, I'm going to isolate for A because that's what I want. And then the force of gravity on this object while it's on this incline is going to be mg sine of theta, or I'll just write the degree already, so it's going to be 65 degrees. So rewriting this with everything that we have, we will have that the acceleration is equal to mg sine of 65 degrees all over the mass. These masses will cancel out, so then we're left with the acceleration equals to g sine of 65. So that's 9.8 sine of 65 degrees. And then you'll get that your acceleration is equal to 8.8818 meters per second squared. Now we can go ahead and write that over here, 8.8818 meters per second squared. Now that we have our acceleration, we have three variables, so we can solve for the other missing two, but in this case we only care about the velocity final. So now we could go ahead and solve for the final velocity, and for this one we are going to use the equation v final squared equals v initial squared plus 2a, and it would be delta r since that's the direction that we're moving in. And now we want v final. So what we're gonna do here, so also we know that v initial is 0, so we could just cross that out already. And to get v final by itself, we would just square both sides. So then we would have v final equals the square root each side, 2a delta r. Here we already know everything here, so we could just go ahead and plug that in. V final equals the square root of 2, our acceleration that we got from the last step, and delta r, which is 2 meters. And once you plug that into your calculator, you will get that the velocity final is equal to 5.9604 meters per second. And just on the exam, make sure to write down the ramp. So the direction. And that is it for that problem. Coefficient of kinetic friction is 0.750. What will be the speed of the mass after sliding 2 meters down the incline when starting from rest? So this part is almost exactly the same as the previous part, just that in this one we have an extra force. So let's go ahead and do the exact same steps that we did. So we have the sum of all the forces is going to be equal to the mass times the acceleration. Isolating for acceleration, we get this. And now we're going to write down all the forces that we actually have. So we're going to have the force of gravity in the positive direction, in the direction that we're moving. And then we're going to have the force of friction in the negative direction because it's going to be opposing our motion. I should have wrote it like this. The force of gravity minus the force of kinetic friction all over m is going to be equal to our acceleration. Now we can expand these. So our force of gravity is going to be equal to mg sine of theta minus the force of kinetic friction, which is going to be the normal force multiplied by the coefficient of friction, which is this one right here. And the normal force in this case is going to be the perpendicular component of the gravity. I think that's how you say it. Anyways, it's gonna look like this. So we have mg cosine of theta and then times mu k all over m. Notice here that we can pull out the mg's. Oh, this is gonna be equal to acceleration. So we have mg sine of theta minus mu k. I'm gonna bring the mu k to the front. Cosine of theta all over the m. The m's here will cancel out. So then we are left with the acceleration is equal to g sine of theta minus mu k cosine of theta. And writing in all of our values, that's going to be 9.8 sine of 65 minus mu k, which is 0.750. Cosine of 65. And once you plug that into your calculator, you should get that the acceleration is equal to 5.7755 meters per second squared. And now here we are just going to do the same thing that we did over here with the kinematics. So what we really care about is the acceleration. So I'll go ahead and erase all of this. Okay, so we know that this is our new acceleration. Our velocity final is what we're trying to look for. Our velocity initial is still going to be 0, and our displacement is still going to be 2 meters down the ramp. So I'm going to use the same equation. I'm going to use this one right here, the same formula. I'm going to pull it and use it over here. So I just plug in all my values. So velocity final is going to be equal to the square root of 2. The only thing that's going to change is my acceleration multiplied by delta r, which is 2 meters. Plugging that into the calculator, you will get that the final velocity is 4.8064 meters per second. And again, on the exam, you want to write that is down the ramp. Because if you don't write that it's down the ramp, a person that's like grading your test, let's say we have the object right here. A person that's grading your test, they could think like you didn't write a direction, so they're gonna think like, is it going down the ramp or up the ramp? So just make sure that you have the direction mentioned on your final answer. So that is the answer. That is the final velocity when friction is present. The final part of this problem says what applied force directed up the incline would be needed to produce an acceleration of 2 meters per second squared up the incline. Friction is present and mu k is equal to 0.75. So now we're actually given the acceleration and we want to look for the force. Specifically, we want to look for the applied force. So let's go ahead and write. So we're going to start with Newton's second law. We know our mass and we know our acceleration. So we can just go ahead and solve for that right now. Our mass is 3 and our acceleration is 2. So then this is going to be equal to 6 newtons. Now we could write down all the forces that we're going to have present. So when this, I'll use this drawing. So this block is going to be going up this way now. And the force applied is the one that's going to be pushing it up. And the forces that are pulling it down or opposing this motion, the force that is pulling it down is going to be gravity. And the forces the force that is trying to stop it is going to be friction. So let's write that down. So we have the applied force minus the force of gravity minus the force of kinetic friction. And that is going to be equal to 6 newtons. Now we can go ahead. So we're trying to solve just for the applied force. So we can go ahead and move these two guys over here. So we'll do that by adding the force from kinetic friction and the force of gravity. So now we have the applied force by itself. And now what we're gonna do is we're just gonna plug everything in because we already know all of this stuff. So let's just go ahead and plug it in. So our applied force is gonna be equal to 6 newtons plus the force of gravity. That's gonna be pulling it down. So the force of gravity parallel to the motion, right? Parallel. Okay, so that's gonna be mg sine of theta plus the force of kinetic friction, which is going to be the normal force times times mu. So the normal force is going to be the component of gravity that is perpendicular. So that is going to be mg, not sine, mg cosine of theta multiplied by mu k. And now we have all of these values, so let's just go ahead and plug them all in. So our force applied is going to be equal to 6 newtons plus the mass, which is 3, multiplied by gravity, which is 9.8. I'm not going to write all the units in there just to save space. Sine of theta, which is 65 degrees. Plus mg cosine of theta times mu k. Mu k is 0.75. M is 3. G is 9.8. And that multiplied by the cosine of 65. Plugging that into your calculator, you should get that the applied force should be equal to 41.9641 newtons, and that is directed up the ramp. Moving on to problem number 3. A 0.020 kilogram sphere is held at rest within a fluid. At time equals 0, the mass is released and proceeds to fall straight down through the fluid. The fluid exerts a resistive force on the object that is proportional to the object's speed. At time equals 0.25 seconds, the mass is at 80% of its maximum speed. So we have like a ball dropped in a, I don't know, pool. All right, so the part A is asking us what is the time constant of the system. So the time constant. So first, let us recall um the formula that we know that we're given, which is um the function for the function to get the velocity of this ball at any given time, which is v of t equals v terminal multiplied by 1 minus e to the negative bt over m. Now, we want to get tau out of this. And if you remember, tau is equal to m over b. Right here we have b over m, so not m over b, but what we can do is we could flip both of these fractions. So we'll have that 1 over tau is equal to b over m. And that's what we have right here, b over m. So now we can rewrite this whole thing with the tau instead of the b over m. And tau is going to represent our time constant. So now we have v of t is equal to v terminal 1 minus e to the negative t, and then we're replacing that b over m with 1 over tau, so that's 1 over tau. And now we have tau. So now what we're going to do is solve for tau with the given information. So we know that the object speed at time equals 0.250 seconds is 80% of its maximum speed. So that is some good information. We could write that out over here. So v of 0.25 is going to be equal to vt 1 minus e to the negative, and then the time, which is 0.25, all over tau. And this is also going to be equal to 80% of the maximum speed. So we can write that over here as 0.80. I'm gonna convert it to a decimal, so 0.80 VT. Now what I have is these three things that all equal the same thing. And now I'm just gonna ignore this one because I'm not gonna do anything with it right now. So I'm just gonna focus on these two that we have right here. So we'll have VT 1 minus E to the negative 0.25 over tau equals 0.80 VT. Notice how both of these guys have VT, so that is going to cancel out. Now we have 1 minus e to the negative 0.25 over tau equals 0.80. And again, we are solving for tau, so we want to get tau by itself. What I'm going to do is I'm going to subtract the 0.8 and add this e. So I'm just going to skip that step because I don't want to write all of that. but I'm going to go ahead and rewrite it over here. So it's going to look like 1, and then minus that 0.80 is going to be 0.20. 0.20 is equal to E negative 0.25 over tau. Now to undo this E, we have to take the natural log of both sides. So we're going to take the natural log of that, natural log of that. So then now we are left with the natural log of 0.20 equals negative 0.25 over tau. We want to get tau by itself. So what I'm going to do is I'm going to first multiply both sides by tau. So now we have tau, the natural log of 0.20 equals negative 0.25. And now again, tau by itself, so now I'm going to divide by the natural log of 0.20. And once you put that in your calculator, you should get that tau is equal to 0.1553 seconds. So that is the duration of one time constant, or the time constant for this specific problem or this specific system. All right, the next part B, is asking what is the speed of the mass at time equals 0.125 seconds. So for this part, we are actually going to use this function again. So I'm going to rewrite it over here. So V of t is equal to V terminal multiplied by 1 minus e to the negative t over tau. I'm going to keep tau in there because I already know tau and it makes my function a lot simpler. So now we have all of these things except for V terminal. However, we were given a formula to find V terminal, which is V terminal is equal to the mass multiplied by gravity all over B, which is the constant of proportionality. And now what we're going to do here is we are going to solve for Vt. And going back to this again, we know that tau is equal to m over b. We have m over b right here, so we'll just replace this m over b with tau. So then we'll get that Vt is equal to tau times g. We know tau and we know g. So then V of t is equal to tau, which is 0.1553 seconds multiplied by g, which is 9.8 meters per second squared, and you will get that the terminal velocity is going to be 1.5222 meters per second. That is very important because now we can plug this in right there and we can solve for the velocity at this specific time. So let's go ahead and plug that in. So the velocity at 0.125 seconds is going to be equal to V terminal, which we just found to be 1.5222. I'm going to keep the units out for right now, or until the end, just to save some writing, or save time on writing. 1 minus e to the negative time that we have. So we have negative 0.125 seconds all over tau, which we found in the last part, which is 0.1553 seconds as well. Once you plug all of that into your calculator, or you do it in your head, you will get that the velocity at 0.125 seconds is going to be equal to 0.84146 meters per second. Well, this one is asking for the speed, but the velocity is, hold on, the velocity is not the same thing as the speed, but the speed is just going to be the absolute value of this, which this is already positive. So it's going to be, the speed is going to be this, just that, yeah. All right, so the last part of this problem says, at what time is the resistive force acting on the mass equal to 90% of its maximum value? So what we have to do is we have to relate the resistive force with time. How we're going to do that is with this formula right here. So the resistive force is going to be equal to BV, where B is a constant of proportionality and V is this thing that we have right here. V of t, this function that we have, V of t is all of that. And then we have that time right there. That's what we're going to look for. So before we just start plugging things in, we first need to find what R is. And R is going to be easy to find because we are told that it's at 90% of its maximum value. And we know that the maximum value of R is just going to be mg. So R is also mg. And that we can just go ahead and solve for. So the mass is 0.020. And then multiply that by gravity. I'm going to keep the units out just so that I don't have to write everything down. Now that we have that, we go ahead and solve that out and we'll get that. Also, by the way, this is R max. R max is equal to mg. And we will get that is equal to 0.196. 0.196 newtons. I'll add the units to the end. So the maximum force is 0.196 newtons. And now we can find 90% of that by multiplying it by 0.90. So that's going to be 0.196. That, if we plug that into our calculator, we will get 0.1764. 0.1764. Okay, so now we know what 90% of that is. So we know this, we don't know that, and this is what we're going to try to look for. But we can actually find B by using this equation over here, this formula right here for tau. We know tau, we know the mass, we don't know B, but we can rearrange to get B. Multiplying both sides by B and then dividing both sides by tau. We will get that B is equal to the mass over tau, which if we write it out, B is equal to the mass, which is 0.020 over tau, which is 0.15533, which is then going to be equal to 0.12875. So now going back to this formula right here, we have R, we have B, we don't have V, but V is what we're looking for, so we can rearrange this to isolate for V. And actually we can use this, well, oh, you'll see right now. So we have R equals BV, isolating for V, we divide by B, divided by V. So now we have that V is equal to R over B. And what I'm going to do here, just so I don't have to carry around these variables, is I'm just going to go ahead and solve for V already. So we know that R is equal to this one, because we're looking at 90% of the maximum, not the maximum. This is also in newtons, my bad. So we have 0.1764 all over B, which we just found to be 0.12875. 0.12875, and that will get you a velocity of 1.37009 meters per second. Now we have the velocity. Now we can set the velocity equal to this equation right here, and we know everything here. We know Vt, we know tau, we just isolate for t. So now let me save that because I'm gonna need that. Could erase all of this because I'm not gonna need it anymore. So now I'm gonna set the velocity function equal to this. So we'll have 1.3700 9 is equal to the terminal velocity 1 minus e to the negative t over tau. And now here it's pretty straightforward, just solve for t. So the first thing that I'm going to do is I'm going to divide by vt, or the terminal velocity. So now I have 1.3009 over the terminal velocity is equal to 1 minus e to the negative t over tau. And here I'm going to add e to this side and subtract 1.3009 over vt on this side. So that is going to look like this. We have e to the negative t over tau is equal to 1 minus 1.3009. I forgot a 7 here. 7, 7. All over, not over, but just this part is going to be over vt. Now to get rid of this e, I'm going to take the natural log of both sides. So the natural log of that side, the natural log of that side, we are going to be left with negative t equals tau. Negative t over tau equals the natural log of 1 minus 1.37009 over vt. And now here, to finally isolate t, I'm going to multiply both sides by negative tau. So then we'll have that the time is equal to negative tau multiplied by the natural log. The natural log of 1 minus 1.37009 all over the terminal velocity. And I know all of these values, so I'm just going to go ahead and plug those in. Time is going to be equal to negative tau, which is 0.15533 multiplied by the natural log of 1 minus 1.37009 all over the terminal velocity, which we found over here to be 1.5222. And plugging this into your calculator, you'll get that the time is equal to I actually forgot to write it down right here, but I have it on my calculator, and it is equal to 0.35777 seconds. So that is the time where your resistive force is going to be at 90% of its maximum value. Bet. Moving on to problem number 4. It says a mass of 3 kilograms is initially at rest upon a horizontal surface. An applied force of 15 newtons begins acting on the mass, directed at an angle of negative 25 degrees with respect to the positive I direction. There is friction also acting as the mass slides across the surface. Part A is asking us what is the work done by the applied force over a distance of 2.5 meters. This one is pretty basic. We're just going to use the work formula. And since the applied force is constant, it's just going to be just no integrals, just work equals force times distance. It's that easy. So work is going to be equal to the force, which is negative 25, which is at an angle of negative 25. So we're going to do 15 cosine of negative 25 degrees multiplied by the distance, which we are told is 2.50 meters. And I'm doing cosine of negative 25 degrees because we only care about the horizontal component of this this applied force in this part because we don't care about the vertical component because the mass is not going to be moving up or down. It's just going to be moving left or right. So we only care about the force, the component of the force that's making it move left and right. So therefore, you plug that into your calculator and you will get that the work is equal to 33.9865 joules. And similarly, with part B, it's going to be the exact same thing, just that now we're working with a different force. So if the coefficient of kinetic friction mu k is equal to 0.650, what is the work done by the force of kinetic friction over the distance of 2.5 meters? So again, the force of kinetic friction is going to be constant, so there's no integrals here. We're just going to do the simple formula: work equals force times distance. Now we have work equals the force. However, not only do we have okay, so the force of kinetic friction is equal to the normal force multiplied by mu k. For the normal force, we're gonna have mg, but we normally just have mg, but we are told that we have an applied force and it is at this angle. So there's gonna be a vertical component of this applied force, so we have to include that over here. So it's going to be minus whatever that is, which is going to be the vertical component, so that's sine of negative 25 degrees. Now let's go and plug all of this over here. So we have mg minus the sine of negative 25 degrees multiplied by mu k, which is 0.65. And yeah, here we know everything here, so we can just go ahead and solve. And again, this whole thing is all equal to the normal force, because the normal force now has to not only fight against gravity, but it also has to fight against this applied force. So going and plugging in everything that we have the mass, which is 3, gravity, which is 9.8, minus the sine of negative 25 multiplied by the coefficient of kinetic friction, which is 0.650, and plugging that into your calculator, you will get that the work done by kinetic friction is, oh, I forgot to mention here. So this force, going back over here to the force of kinetic friction, is gonna be negative because the force of kinetic friction is fighting against the motion, so it's gonna be in the negative direction. So I forgot to mention that there's gonna be a negative right there, and so negative right there, negative right there, negative right there, and um okay, so then we have this. So we have the negative. We plugged the negative back in there. I mean, not back in there, but we plugged it in because it should have been there in the first place. So now we have that the work is equal to negative 58.076 joules, and that makes sense because negative means that it took out energy, or it did negative work. So yeah, that makes sense because friction is like slowing the thing down. So it should be negative. It should not be positive work because it's not helping the applied force. Problem number 5 says of 0.4 kilogram mass is initially traveling at a rate of 20 meters per second while sliding across a horizontal surface. It is initially 3 meters from the end of a spring laid horizontally that it will eventually contact and compress. Friction is present and the coefficient of kinetic friction is 0.750. So we're going to go ahead and solve for part A, which says, what is the speed of the mass as it reaches the spring? Um, you can do this part using just kinematics, but I'm gonna go ahead and do it with work because the other following parts, part B and C, are also gonna be using work. So I just want to keep it like consistent. So to solve this one, what is the speed of the mass as it reaches the spring? First, I'm gonna write the work energy theorem. So the sum of all the works is gonna be equal to the change in kinetic energy. The change in kinetic energy has our final velocity, so that's why I'm starting off with this. The sum of all the works, the only force here that's going to be doing work is the force from friction. So then we have the force of, I'm gonna go ahead and expand it already. So we have the force of friction times the distance, or I'll do delta x. It's gonna be equal to kinetic energy, which is 1/2 mv final squared minus 1/2 mv initial squared. Now here I'm gonna go ahead and isolate for this v final because that's what I want. So I'll do plus 1/2 mv initial squared, and I'll add this on this side as well. So then I'll have that 1/2 mv final squared is equal to this, which is the work done by friction, plus 1/2 mv initial squared. Now again, I want to isolate for VF, so I'm going to multiply both sides by 2. And then after that, I'm going to divide both sides by m. And then finally, I'm going to take the square root of both sides. I know it's a lot of steps, but it's going to look like this in the end. So velocity final is equal to 2 times the work done by kinetic friction plus 1/2 mv initial squared all over m, and then the square root of all that. Now, this is how it's going to look, but we have to be careful with this force of kinetic friction because the force of kinetic friction is going to be equal to the normal force times mu k. So we can go ahead and expand that out even more, but also we have to take into account that the force of kinetic friction is opposing this motion. It's like stopping the object, so we're going to make it negative. So then now we can go ahead and write all of this new stuff. So we have velocity final equals the square root of 2 times the normal force, which is going to be equal to mg. I'm going to go ahead and write that negative already. Mg mu k multiplied by delta x, which is, we'll write it later, but delta x plus 1/2 mv initial squared all over m. Now we can go ahead and write all of our units in here. So velocity final is going to be equal to 2 negative m, which is 3, g, which is 9.8, and then mu k, which is 0.750, and then delta x, which is 3 as well. Wait, no, that is 3. This is 0.4. Like that. 3 plus 1/2 the mass, 0.4. And the velocity initial squared, we are told the velocity initial is 20. 20 squared. This all over the mass, which is 0.400. And once you plug all of that into your calculator, you will get that the final velocity is equal to 18.865 meters per second. All right, so the next part of this problem says if the spring is then compressed by a maximum amount of 0.025 meters due to the mass contacting it, what is the spring constant of the spring? So for this one, again, we're going to use work, and specifically, we're going to use this formula that tells us that the work done by the non-conservative forces is equal to the change in potential energy plus the change in kinetic energy. And this change in potential energy is what's going to have the spring constant. So that's why we're using this one. So let's go ahead and expand this before we plug anything in. So we have the work done by non-conservative forces is equal to the change in potential energy, specifically spring potential energy, which is 1/2 kx squared, and then kinetic energy, which is 1/2 mv squared. So let's go ahead and write that. So we have 1/2 kx final squared minus 1/2 kx initial squared plus, I'll erase this, 1/2 mv final squared minus 1/2 mv initial squared. And now from here, we can go ahead and isolate for, or we can cancel a couple of things out. So we know that once the spring is fully compressed, that means that the mass it's not moving anymore. So we can say that the velocity final is going to be equal to 0. So then this whole thing will be equal to 0. So we could cancel that out. And also in the beginning, the potential energy of the spring is at 0 because it's not extended at all or compressed at all. So this would be 0. Then that would make that whole thing 0. So we could cancel those two out, and then our new thing is going to look like this. So the work done by the non-conservative forces is equal to 1/2 kx final squared minus 1/2 mv initial squared. Now here now it looks a lot nicer. Now we could go ahead and isolate for k. So we'll add this to both sides. And we will have that the work done, that 1/2 kx final squared is equal to 1/2 mv initial squared plus the work done by the non-conservative forces. And now again, isolating for k, we will multiply both sides by 2 and divide both sides by x squared, or x final squared. So then we'll get that k is equal to 1/2 mv initial squared plus the work done by the non-conservative forces multiplied by 2 all over x final squared. And now here we know everything in this, everything that we need, and we can expand this work done by the non-conservative forces. So the work done by the non-conservative forces, we only have one non-conservative force here, or yeah, we only have one non-conservative force in this problem. So that's going to be friction. So it's just going to be the work done by friction. So the work done by friction is going to be Fk times the distance. I'll call it delta x. And again, since friction is acting against this system, it is going to be acting against this system. It's going to be negative. So then the work done by the non-conservative forces is negative, and then The force of friction is given by the normal force times mu k, or mg times mu k. So then it's going to be negative mg mu k multiplied by delta x. And we can go ahead and plug that in right here. So then finally we'll have k equals 1/2 mv initial squared plus what we got over here, so we would change that to a minus mg mu k delta x, all of that multiplied by 2, and then divided by x final squared. And from here we can just go ahead and plug everything that we have, and this x final squared really represents the displacement that the spring went through, or the displacement of the spring. So x final is going to be equal to how far the spring was compressed or stretched, which right here we're being told that it's 0.025 meters. So I'm going to go ahead and erase all of this so I have room to write. So now plugging in all of our values, we will get that k is equal to 1/2 the mass, which is 0.4, times the velocity initial squared. The velocity initial squared is, where'd it go? 20 meters. 20 meters per second. Minus mg, which m is 0.4, g is 9.8, multiplied by mu, and then multiplied by delta x. Mu is 0.75, and then delta x in this case is going to be the same amount as x final, or the same amount that the spring is compressed. So that's going to be 0.025, and then all of that is multiplied by 2. I'm not sure if I got all of my parentheses right, but multiplied by 2 all over x final squared, which is this right here. So that's 0.025 squared. And once you plug all of that into your calculator, you should get that k is equal to 227540.8 Newton meters. The final part C, says, with what speed will the mass then leave contact with the spring as the spring returns to its equilibrium position? So to do this one, we're going to use the same formula as the last part, which was the work done by the non-conservative forces is going to be equal to the change in potential energy, specifically spring potential energy, plus the change in kinetic energy. And it's asking us with what speed. So we want the final velocity, and that is going to be found in this one right here. So I'm going to go ahead and expand this. So we have the work done by the non-conservative forces is equal to 1/2 kx final squared minus 1/2 kx initial squared plus 1/2 mv final squared minus 1/2 mv initial squared. So now we have our v and v final. That should be an f. V final squared. So now we have our v final squared. Now we just need to isolate it. And before we do that, we can cancel out some things. So let's look at the problem again. With what speed will the mass then leave contact? Okay, so it's going to have a speed at the end, but at the beginning it has no speed or no velocity. So that's going to be right here. The initial velocity is going to be equal to 0. So if you plug in 0 right there, that whole thing will just cancel out. And as the spring returns to its equilibrium position, so the spring is initially compressed, but then um, once this whole problem goes on, or once this thing happens, the spring is going to go back to its equilibrium position. So its final position is just going to be 0. So we can go ahead and cancel that out as well. And now we're just left with these two. So we will have that the work done by the non-conservative forces is equal to 1/2 mv final squared minus 1/2 kx initial squared. Now here we can go ahead and isolate for v final. I'm going to go ahead and add this one to both sides. So then we'll have that 1/2 mv final squared is equal to 1/2 kx initial squared plus the work done by the non-conservative forces. And again, we're isolating for v final, so we'll multiply both sides by 2, and then we'll divide both sides by this m. And then finally, we'll take the square root of both sides. So now we have v final is equal to 1/2 kx initial squared plus the work done by the non-conservative forces multiplied by 2 all over m, and then the square root of all that. And again, we're going to expand this work done by the non-conservative forces. So the work done by the non-conservative forces, we only have one non-conservative force here, which is the force of friction. So that's what we're going to write right here. So it's going to be the force of friction multiplied by the distance. And the distance here in this case is going to be, I should have written it down, but it was 0.025 meters. Now, we can go ahead and expand this out even more. We know that the force of kinetic friction is equal to the normal force multiplied by mu k, which is then equal to mg multiplied by mu k. And since we know that this force of kinetic friction is going to be acting against our system, that's going to be negative. So then the work done by the non-conservative forces is equal to negative mg multiplied by mu k multiplied by this delta x. So now we can go ahead and rewrite that over here. I'm going to erase this. I'm going to erase all of it. Okay, so now we have that the final velocity is equal to the square root of 1/2 kx initial squared, and then we're going to plug in that thing that we got for the work done by the non-conservative forces, so that's minus mg mu k delta x, all multiplied by 2. I forgot to put on, actually I didn't. Okay, all multiplied by 2, and then all divided by m, and then we take the square root of that whole thing. So now that we have everything that we need, and we have v final isolated, we can just go ahead and plug in everything that we know and solve for this. So that's 1/2 k. We found k in an earlier problem. I should have wrote it down somewhere right here. But that is equal to 540.8. K, and then x initial squared. That's gonna be, over here we know that it was compressed by this much, so 0.025. 0.025 squared minus mg, the mass of this object is 0.4, gravity is 9.8, mu k is 0.75, and then the delta x is 0.025. All of that multiplied by 2. And then all of that divided by m, which is 0.4. And you'll get a final answer of the final velocity is equal to 18.845. And if you remember from our part A, the initial velocity was actually 18.865. So this object came in faster and left slightly slower. So that just proves that friction did do negative work. It took out energy and it slowed this object down.